Good afternoon, everyone. This is Mr. Couple. Today, I will be continuing our discussions about magnetism, but today we're going to be getting into electromagnetism. So, we'll be discussing how electric currents can create magnetic fields. There are three main ideas for the lesson today. So, the first up is I want to talk about Ørsted's discovery. The second thing I want to do is talk to you about the right hand grip rule. And then the last thing is I want to discuss electromagnets and how you can strengthen them based on two things, either increasing the current or by increasing the number of loops. Let's begin. In 1820, there is this physics teacher. His name was Hans Christian Ørsted. There's a picture of him. He was giving a lesson in his physics classroom, and he was talking about electric currents. And he just so happened to have a couple, days before been talking to his students about magnetic fields and compasses. And so he still had this compass lying out. And here's a picture of like a compass. And then what Ørsted did, it was like the next lesson, he was creating an electric current. And so what happened was he actually ran a current through a wire nearby to this compass needle. And what he found was really startling and shocking, and he was surprised by it. So here's the idea. Right now the compass is lined up with the Earth's magnetic field. You can see the north poles pointing up to the left. We're going to take this wire. There's no current in the wire yet. You can see the battery's disconnected. But watch what happens when we connect the battery and run a current. Whoa, the compass needle gets deflected. So this is what Ørsted noticed that day that he was giving this lesson, is he noticed that a nearby compass was deflected by the current that he had sent through the wire. So this is Ørsted's discovery. It's a really big deal because the entirety of modern electronic devices and all of our high-tech society is literally based on this one discovery. I mean, it might not seem like it's that exciting, but I assure you, like all of modern society is based on this discovery. And it was discovered by Hans Christian Ørsted in 1820. So I want to talk about this. So the explanation is that, the compass needle has two forces on it. So there's a force in it pointing this direction because of the Earth's magnetic field. So that's the force from the Earth. But then the wire is creating a magnetic field, the current in the wire, I should say, the current flowing through the wire. So when we connect this and current starts to flow through the wire, current's going to flow this way. So when the current starts to flow through the wire, it actually creates a second force on the compass pushing it this direction. And so that's the force from the current. And then you can see that those two forces add together, pushing the compass needle in this direction. So that's what's happening, is that we have this discovery that electric currents create magnetic fields. And this was a revolutionary discovery. It's a really big deal. So here's the question. Why does a current carrying wire deflect the compass needle? So how could it be that a wire with a current running through it, why would electricity create a magnetic field? So there are three things I want to reveal one by one. Here we go. So first, a current carrying wire contains many charges moving all in the same direction. So you have the wire, and then all the charges in that wire, they're all moving together in the same direction. They're not like randomly moving around because we have a current. That's what a current is. They're all flowing together. Okay, next. We'll remember this from last lesson, is that in addition to electric fields, moving charges also create magnetic fields. And so each one of these charges in the current is in motion, and each of them is going to create a magnetic field. And so the space around the current carrying wire is going to have a magnetic field created by these moving charges in the current. So that's, just think about it, like a current is just moving charges, and moving charges create magnetic fields, and so currents create magnetic
I
fields.
can't see the screen.
So
I
is it?
can't see the screen.
I will restart. Oh, wrong button. Let's see, I gotta go to Discord. I gotta turn this off. Turn it back on again.
Stream is dead. Long live the stream.
Yes, indeed.
Okay,
So why does a current create a magnetic field? Well, it's because moving charges create magnetic fields, and a current is just a bunch of moving charges. And so that makes sense then that each one of these charges is going to be creating a magnetic field. Let's investigate this a little bit further. So here are some additional experiments we can do. So here's the first one. We're going to take a wire. This is going to measure the current down below. This is called a multimeter. I don't think I ever talked to you guys about those. If we were in the lab, we would have been using them. So we connect this multimeter to this wire, and we're going to run a current through it with a voltage source. We're going to run a current through this wire. And the compasses are going to be placed strategically around the wire to try to show us the magnetic field. So here we go. So you can see that as soon as we turn on the current, so once the current is turned on, the compasses align themselves with the magnetic field. So in the beginning, there is no current, so the compasses are just pointing with the Earth's field. But as soon as we turn on the current, the compasses align themselves with the magnetic field. So the question is, what shape is this field? So every year I have students say it's a square. Do you guys think it's a square?
It's a circle.
It's a circle. Yeah, it makes more sense to say it's a circle. Mayra, what were you going to say?
I was just gonna say that it wasn't.
Yeah, it's not a square. So let's do another experiment. So this is a video that I took at a place in San Francisco. I went there about 2 years ago. It's called the Exploratorium. And I saw this apparatus and I just knew I had to take a picture of it and record a video of myself playing with it. So I'll show you guys that video. Well, if you can't tell, instead of just 4 compasses, there's a whole field of compasses set up around this wire. So I'll show the video to you guys. Okay, so over there I have a power source, so I can turn it on or off. And when I turn it on, you can see that all the compasses line up with the magnetic field created by the current. So that's pretty cool. And then I'm going to show you, I turned it off, they all go back to normal again. And so there we go. I can make the current go up or down. One last experiment. Well, what about instead of compasses, why don't we just use a bunch of iron filings, like thousands and thousands of little teeny tiny iron filings, because each iron filing is essentially a tiny little compass. And I should explain what's going on here first. Okay, so this is a wire. What's up? Not working again?
Yeah.
Oh, geez.
Yeah. Mayar, was it okay for you?
It was okay on my end. Was it okay on your end the last time?
Yeah, it was okay on my end last time.
Keppel, this must be fun for you.
Yeah. I tried to get YouTube streaming to work, but it kept saying like it takes 24 hours to authorize it, and I was like, what? So I just gave up. Okay, anyway,
How
so
about Zoom but cameras?
I don't want to use Zoom. I'm against Zoom. Okay, so we have this wire here, and it's kind of hard to tell, but this is actually going into the screen. So there's a wire that's going to the right, and it's going in. So it's actually going into your screen. Okay, I'm going to hit play on this, and then watch what happens when you turn on the current. So you can see that the magnetic field around the wire is now pulling all those iron filings and causing them to line up with the field. And so we can very clearly see here that the field around a current carrying wire is circular. I think at the very end of this video, it pulls back and you can see, yeah, there you go. So you can see that the wire was coming this way and then going in like that. And the filings were just showing us a cross section of the field. So here are the conclusions from these experiments. The magnetic field, we use the symbol B, capital B for magnetic field. The magnetic field around a current carrying wire forms concentric circles around the wire. And the strength of the field diminishes with the distance from the wire. So that's a lot easier to see in this picture here. So you can see that the inner circles, the inner fields, are much closer together than the outer field is. And the further and further you get, the more and more spread out those field lines are going to be, showing you the weaker and weaker the field is. But the main idea here is that you have a current flowing through this wire, and then that current is creating this magnetic field around the wire. This is very similar to a picture I showed last time with a single charge. So here we have one positive charge moving to the left, and you can see that the field around it is creating these circles. Now the difference is that with a current, you don't just have one charge, but you have kind of like a train of charges. Like you have a whole bunch of charges that are all moving together. With a single charge, you'll notice that the field gets weaker ahead of the charge, like because it's moving that way. So the field gets weaker ahead of the charge and it gets weaker behind it. And then the strongest is right here next to it, where the field is the strongest. And so you can imagine then that if you had a whole train of those guys, like you had a whole bunch of them going together in this line, then there wouldn't be any weak spots. Like the field would just be like strong all the way across. So it said a moving charge creates a magnetic field in the space around it. Magnetic field lines form circles around a moving charge, and the strength of the field diminishes ahead of and behind the charge. Okay, so this brings us to something I've been dreading to try to teach through the online environment. It's called the right hand grip rule. And students usually struggle with this for a while until I walk over and like grab their hand and like pull it around and show them how to do it. Students have a really tough time with this, so don't get upset if you have difficulty with
Uh,
this. What's up, Ben?
there's a Vsauce video that talks about this, so
Nice.
that that helps.
That's really good. Yeah, it's gonna be really tough for me to like show you this right hand grip rule, but hopefully I have a ton of pictures that I'm gonna show you. So hopefully after all this it'll make some sense. So here's how you do it. So we created this right hand grip rule. Make sure you're using your right hand. This is my right hand. I don't know if you can tell this is my right hand on the video, it might be flipped, but you use your right hand and the thumb, you orient it so that the thumb points in the same direction as the current. So if the current is pointing up, we're putting our thumb up. And then because of the way that your anatomy works, you could only, if your thumb is pointing up, you can only move your hands in one direction. Your fingers can't naturally, they can't go the other way. So if you put your thumb up, your fingers are just going to naturally curl around. And then when they curl like that, when your fingers curl, they're going to curl in the same direction as the magnetic field does. And so this is the right hand rule, and it's what we use to relate the direction of the current with the direction of the magnetic field that it creates. So remember, your thumb is the current, and your fingers, see how that looks like a field? Your fingers are the field. Before I get to solving some problems with this or showing you guys how this works, we have to realize that there's actually a dilemma here. Magnetic field lines are three-dimensional, but a piece of paper or a screen that you're watching this on is only two-dimensional. So how do we draw a three-dimensional field, or how do we represent directions in three dimensions on a two-dimensional sheet of paper? So this paper only has two dimensions. The dimensions are the horizontal and the vertical, or in mathematics you call it the x and the y direction. But we need a third dimension. Bloop. We need a third dimension coming out of the page. So we want to be able to draw an arrow that's pointing out of the page or an arrow that's pointing into the page because we want to be able to represent all six directions that you can point. So I can point up, I can point down, I can point left, I can point right, but we need new directions for going into the screen or coming out of the screen. And so the way we do this is we imagine an arrow. So imagine an arrow is shot and it's heading towards the piece of paper and it's coming towards you. What do you see? You see the dot on the tip of the arrow. So this symbol, a circle with a dot inside of it, we use that symbol to mean it's an arrow pointing out of the page. So you imagine that that dot is the tip of an arrow and it's coming towards you. Likewise, you can imagine an arrow going away from you. You will see the fletching. And so the fletching kind of makes this like X shape. And so that's an arrow going into the page. So it's like coming out of the surface. So it's coming out of the paper towards you or away. I'm trying to say it's what am I doing, guys? I'm like completely saying this wrong. So
Nobody knows.
dot
Take
means
your
it's
time.
coming towards you. The X means it's going in. You're seeing it go away. It's like going into the page. I can't. How do I draw it going in? I don't know how to do that with my hand gestures. Okay,
Oh,
let's try to explain this. What's up?
well, I have a question.
Yeah.
So the dot is like the arrow is getting shot at you, where like the X would be like if you were shooting an arrow, that's what the other
Yes.
person who was on the
Yeah.
other side would see.
If you saw it,
Wait,
yeah, yeah,
that's
yeah.
right.
Well, okay, wait. So if you shoot an arrow, which one are you gonna see when you shoot the arrow? You're gonna see the X.
Yeah,
The person that you're shooting it at, they're gonna see the dot.
yeah.
Yeah. So the dot means it's coming towards you out of the page, and the X means it's going into the page.
Yeah.
Okay.
All right,
So what I
give
want to
me a
do now,
second.
what's up?
Not nothing.
Okay. What I want to do now is I want to draw. So this is like a fancy drawing that you know I can't draw. That's too like computerized. But how would we represent this on our paper? So this white polygon over here is supposed to represent the piece of paper. So here's what we do. We're going to draw the wire. So I'm going to draw a circle like this. And then that's going to be the wire. And what I'm going to say is that the current in the wire, let me try this again. The current in the wire, so this is the wire. The current in the wire is flowing into the page. So I'm going to draw an X. So that means that the wire, imagine the wire is like sticking out of the page and the current is going into the page. So I can't, is this the right way? So the current is going into the page. So what that means is I'm going to draw the magnetic field. Well, I know the magnetic field is going to make circles around the wire. And now I just need to figure out what direction the field is going to point. So if I put a compass in this field, which way would the compass point? So we're going to take our right hand, I'm going to take my thumb, and I'm going to point it into the page. How do I even show that? That looks like it's coming out of you. I'm going to point, I can't even do this on the video. I'm going to point my thumb down into the page. Like take your thumb and actually put it into the video, like into the screen. And then you can see that if you rotate your fingers, they'll be going this direction. Your fingers will be rotating clockwise. If you go into the page with your right hand and try to rotate your fingers and I can't even twist your fingers, they'll be going clockwise. This is so hard to do on a video. If you guys could see me doing it in person. Okay, thank you.
It's frozen. Stream is dead.
No.
Oh, stream is not dead. Stream is not dead. Stream is not dead.
Okay. False alarm.
Stream is now dead. Stream is not dead.
Where's my? There it is. You
Wait, no, stream is dead.
You mean to restart it?
No, wait, no. Okay, no, now it's good. Now it's good. Just really.
Okay, so here are 4 wires, and each wire has a current in it. The first one here is just a wire. It's just, a current going side to the side. Which way is that? This way? That way. The other one is a current going down. This one is a current going into the page, and then this is a current coming out of the page or out of the screen. I think I'm gonna say screen. You guys are watching me on a screen, so I'll just say screen. So what we want to do is we want to use the right hand grip rule to indicate the direction of the magnetic field. So if the current is going to the right, I'm going to take my thumb and I'm going to point it to the right. So take your thumb and point it to the right. And then you can see that your fingers have to curl into the page on the top. And then if you wrap around the wire, your fingers will be pointing out of the page on the bottom. And so I've indicated the direction of the magnetic field around this wire. Now we can't show the rest of the field because the rest of the field is actually not touching the page. Like it's coming out of the page, it's making these loops. So the way to visualize it is like this. So I found this visual to show it to you guys to compare these. So you can see that what's happening here is that if we placed a compass above this wire, the compass needle would be pointing, this way because above it's going into the page. And if we put the compass below, like down at the bottom, like down here, if there was a compass there, it would be pointing this direction because the field down here is coming out of the page. Hopefully that makes sense. It's really hard to do on a 2-dimensional screen. Trying to teach this over a video is extremely difficult.
No, it's easy to understand.
Okay, so now let's practice this one. So which direction am I going to put my thumb?
Down.
I'm going to put it down. And then when I curl around the wire, I see that my fingers are going into the page on the left-hand side, which means they have to be coming out of the page on the right-hand side. We already did this one. So for this one, I'm going to put my thumb into the page and then wrap around. And so I'm going to wrap clockwise. So the magnetic field is going to, that's disgusting. I'll just draw an arrow. I'm just trying to indicate the direction. We don't need to worry about like drawing all the field lines. We're just trying to show the direction. That's all I just said indicate the direction of the field. And then for the last one, that is coming out of the page. So this is coming out. So I have to put my thumb up, coming out of the screen, and then you'll see that your fingers will actually curl counterclockwise in that case. Okay, that was difficult. I'm going to keep moving on. All right, let's get more interesting. So what happens if the wire is wrapped in a loop? So we talked about if it's going straight, like you got these circles going in it. But if you wrap the wire in a loop, then what happens is all those fields end up sort of combining together on the inside of that loop. All these fields are going to add together and make a much stronger field. And so this is actually
have evolved.
They have.
They make the giga field. I don't know.
Giga field. So this is really useful because we can strengthen the magnetic field tremendously by making a loop. And so here are examples of that. Now the hard part is that your thumb is supposed to go in the direction of the current, and it's kind of hard to make your thumb go in a circle. I mean, you could do it, but it's not natural. So usually what you do when you have a loop or wire that's looping, you flip the rule. So the right hand rule works backwards or forwards. So if you just flip it so that instead of your thumb being the current, your thumb can be the field and your fingers can be the current. It works either way. The right hand rule can be reversible. You can do fingers or current either way and it will work fine. But what you can see happening is that on one side where the current is coming up this way and the other side where the current's coming down that way, that the field on the inside gets strengthened, it gets reinforced, like they're all pointing the same way. So you get this much large amplified field by making this loop. Okay, let's practice. So this picture over here is to sort of guide us in what we're doing over here. All right, so it says you're given the direction of the magnetic field inside a current carrying loop of wire. Indicate the direction of the current in the loop of wire. Okay, so we're looking at sort of similar situation like this. It's giving us the direction of the field inside here, and then we have to determine which way the current is flowing. So now I'm going to use the reversed rule. I'm going to use my thumb for the magnetic field. So for this one, I have to put my thumb into, because X means in.
I think it froze again.
I'll restart.
All right.
This is annoying.
Yeah.
I'm gonna have to
Yeah,
write.
maybe a little.
I'm gonna have to write a mean email to Discord. No, I mean it's not like I'm paying for this or anything. They're gonna
Karen?
prioritize the people who actually pay for it. Are we back?
I can see.
Okay, good. So for this one, I've got the magnetic field going into the page. This is the B field. And what I want to do is show the direction the current is going to go. So I'm just going to do the opposite of before. So before, we were putting our thumb in the direction of the current. Well, this time I'm going to put my thumb in the direction of the magnetic field, which is into the page. So when I put my thumb in, I'm going to rotate my fingers clockwise. So current is going to flow this direction. So that's the current. The symbol for current is capital I. And then obviously, if the magnetic field if you want to orient the magnetic field the other direction, out of the page, then you're going to need to make the current go the other direction, which is counterclockwise. So this is counterclockwise, and then this one is just clockwise. We usually call it CCW, counterclockwise. So here's a picture of what I just did. So this is like a three-dimensional or a isometric view, like from the side above. So if the current is going that way, you imagine you put your fingers in that way, and then you got your thumb sticking up through here, like that's where your thumb would be. That doesn't look like a finger. How did you like something like that? I don't know. But there it is. One thing to notice is that your thumb is pointing out of the North Pole of this magnetic field.
So I do have a question.
Yeah.
How do we know how to curl our fingers? Like which direction?
You curl your fingers in the way it feels natural. So if you got your hand like this, it does not feel natural to move your fingers this way. It feels natural to close them into a fist.
Yeah, but like what? So how do we know that we
If
should
you're
curl our
going,
fingers in the way that our thumb points up?
so your thumb is the thumb is where you're starting from. So you put your thumb in this way, and there's only one way to move your fingers. If your thumb's the
Oh,
other
so
way,
this isn't the one where. So what happens when your fingers are like the current?
the fingers are the current here. So the fingertips are the arrow. So imagine like this is your finger. These are like your fingertips here. I don't know what I'm trying to draw like fingers. So your fingertips are up there. So you're just going to take your tips and rotate your hand with your fingertips as being the arrow, if that makes sense.
So is this what happens in a loop?
Yes. So that's why we reverse the right hand rule. So instead of having the thumb be the straight wire, we're going to make our thumb be the straight field. So it's much easier for our thumb to be straight here, and then for your fingers to curl around that way.
Oh, okay, thanks.
Yeah, it's kind of a disaster yeah. All right, so here's the question. What if we increase the number of loops? So what if there are more loops? So instead of just one loop, what if we do loop, 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 tons and tons and tons of loops? So if you do that, you create a device called a solenoid. And so what you can see here is that each loop is going to have a field, and then that field gets stacked up and added to all the other fields that are nearby, and you get a really, really strong magnetic field. So I just have a bunch of bullets here. So when a current is run through a solenoid, it creates a magnetic field because it's a current. The current flows in loops, and each loop creates a magnetic field. The magnetic fields from each loop of wire combine to form one big magnetic field. So solenoids produce a much stronger magnetic field than an equal length straight wire. So this is going to be a way of creating a way more powerful magnetic field. This actually is how you make a device called an inductor, which is an electronic device that you'll see inside circuits or circuit boards or electronic devices. You can see these coils of wire. So all of these are coils of wire. They're like loops of wire. Each one of these, that's called an inductor. It's just a solenoid, if you want to call it. That's what we call it when it's not an electrical component. But inductors are just solenoids. Practice. The picture below shows a cross-section of a solenoid. Do you see the solenoid? It's kind of hard to tell.
Kind of.
So what I did is I just cut the wires off, and I'm just looking at the one part of the wire that's going in and the one part that's going out. So like imagine you had like an actual like loop of wire, and I just went shoop and I cut it in half, and I just looked at it from the side. That's what we're seeing here.
That's pretty freaky.
Yeah. So we're going to use the right-hand rule to figure out what direction the magnetic field is pointing. So I'm going to start at the top up here, and I'm going to point my thumb up. So if I point my thumb coming out of the page, then you can see that we're going to curl around this way. So all of these are going to curl this way. So that means that the field inside here is pointing to the right. Just to verify, I can try the same thing on the bottom. That's going into the page. So if I point my fingers into the page here, I'll be curling. Sorry, if I point my thumb into the page here, I'll be curling my fingers this way and coming out that way. And so indeed, that's the direction of the magnetic field. So it's going in on this side, and then it's coming out on the other side. So now we have to figure out which is the North Pole and which is the South Pole. So magnetic field lines. So this is basically a magnet. Magnetic field lines point towards which pole? They point towards
The South Pole.
the South Pole. And they point away from the North Pole. And so that's our South and North Pole. So we've basically just created what's called an electromagnet. So this is called an electromagnet. We have created a magnet using wires and current. A solenoid behaves like a bar magnet. So that's what I was just saying. So the solenoid and the bar magnet are basically the same. They act the same way. The advantages of a solenoid is you can turn it on and off, right? You just flow the current or shut off the current. Switch on the current, switch off the current. So a solenoid can turn on and off. A bar magnet can't do that. It can also be made significantly stronger. So a solenoid can be made stronger. You can just make more loops, or you can run a stronger current. So a solenoid has an adjustable field strength, whereas a bar magnet doesn't. Now the disadvantages of a solenoid is that it requires electricity to operate. So you have to run, it requires energy. Bar magnet doesn't. And it also takes a higher resource cost to actually build the solenoid because you have to construct it out of all the raw materials and stuff like that. But solenoids are basically bar magnets. And what's up, Ben?
I was going to ask what would happen if you put like iron or nickel or something inside of it, and then I saw that was what you were talking about.
So what if you put an iron core? So now what happens is that the solenoid is a magnet. It's creating a magnetic field. And then that field can then align all the magnetic domains of the iron. And now all those iron magnetic domains are aligned. And now it becomes an even stronger magnet. So you can sort of use the solenoid, use the electromagnet to make an even stronger magnet by putting an iron core inside of it. And so here's an example of where when you don't have the iron on the inside, the field is weak. But when you do have the iron inside, the field gets much stronger. And we can see that because there's a lot more field lines. That's a stronger field. However, this isn't, what am I trying to say? Eventually what happens is all the domains inside the iron will get aligned. And at that point, it's not going to get any stronger. That's called saturation. So you want to, the strongest electromagnets don't have an iron core. They use superconducting magnets. All right, so let me show you guys this video of an electromagnet. So basically you just take a nail or some sort of metal object that has domains in it. You wrap a wire around it, and you'll notice that it did not pick up the paper clips. So this nail and this copper wire are not magnetic. They're not, but they are conductors, or the copper is a conductor. When we run a current through it, it can actually magnetize the nail, and now the screw, and now it can pick up paper clips. So now it becomes magnetized, and it's magnetized by the magnetic field created by the current. Man, how did I run out of time?
Mr. Keppel, I'm pretty sure that's what they call a bolt.
A bolt?
I don't think that's not a screw.
It's not a screw. It's a bolt. Thank you, Ben. Man, okay. Thank you. You're right. Thank you.
Same thing.
All right, let's talk about some applications of electromagnets. So there's electromagnets are being used right now because that's how speakers work. You send a current through a wire in the presence of a magnet. So I'll show you guys down here. So here's your wire. So you send a current through this wire in the presence of a magnetic field here, and then that I should have made that a different color. So there's an actual permanent magnet here, and it has a magnetic field coming out like that. And so then the wire also has a magnetic field. And so now those two fields are going to interact, and it's actually going to end up pushing the speaker in and out, creating the sound. And so all you have to do is just vary the current that comes in, like change the properties of that current, like vary the voltage on it or the current in it, and it will then create different oscillation patterns of the speaker and produce all the different sounds that you want to make. You also use electromagnets at scrapyards to recycle metal. Like if you have a big pile of trash and you just want to pull the metal parts out of it, you can use a electromagnet to do that. You can see the wire coming down right there. That's providing the current. And then also in medical imaging, so I know a lot of my students are interested in medical pathways. So this machine's called an MRI machine, and it actually uses really, really strong magnetic fields to take images inside your body. So we can actually like scan people's brains and look inside your body using magnetic fields, which is really awesome. All right, then the last thing I was going to talk to you guys about was these Maglev trains. I know I'm out of time, but I just really want to share this with you. So we can actually create trains that levitate due to magnetic fields. So you have you have magnets on the bottom of the train, which obviously you just get two, you have a north and a south pole, or a north and a north, and they just repel each other. And this will lift the train off the ground. And now the train doesn't have wheels. So in a normal car, right, or a normal train, you would spin the wheel, and then that force would push against the ground, and then the ground would push back, pushing you forward. But how do we push a levitating train forward? And the solution is that we use magnetic fields. What's up?
Hello.
Yeah, I'm here.
Hello.
You can't hear me? I can hear myself.
I can hear you now.
Okay. Were you going to say something about the trains?
The screen froze, and I was going to say how they did it, but
yeah, tell me how.
Like you're going to say, okay. So don't they do it by switching the poles of the track as the train moves? So like the part that's next to it is one pole, but then they switch it as it goes by, so that way then it repels it.
Yep, isn't that awesome? So right now, with this is a south and this is a north, then they attract each other. But notice what happens if the train moves forward to the next one. If that north magnet here moves forward to here, well, now they would actually repel each other. You'd have a north and north, and they would repel. So what you have to do is, as the train is moving along, the magnets in front of it attract it towards it, and then the magnets behind it repel it. And then you just keep alternating those, like swap, 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 swap. You just swap them at the right frequency, and then that actually pulls the train forward. So you're getting pulled forward by the opposite pole ahead of you. You're getting pulled forward by the opposite pole ahead of you, and you're getting repelled by the one behind you. And so that's how you can actually push the train forward. Now, the advantages of a magnetically levitating train is that there's no friction with the ground. You still have air resistance, which is why you have like this nice aerodynamic shape here to try to lower the drag. But you don't have any friction with the ground, which is a huge energy saving. One of the problems is like it's going to require electricity, these electromagnets, to run, and so you just want to make sure that like you're in the end that you're saving energy. But I don't know, it's hard. A lot of people are still working on designing these. There's superconducting magnets that are showing a lot of promise as far as like making these things more efficient. But we don't use them in the United States yet. I believe this one is in Shanghai in China. Okay, I guess I'm going to end it there. I want to plug a video that I'm going to link in the Google Classroom. It's about superconducting magnets. I want you guys to check this out. It's really cool. It's sometimes it's called quantum levitation, but I'm going to link a video for you guys to go watch if you want to learn more about this. Okay, have a great day. It's been fun. See you guys.